West Antarctica. For those of you standing at the back, there are a few spare seats down at the front as well, if you want.
Well, welcome. Thanks very much. My name's Onheiser from the University of Otago, and you notice that's the wrong title. But I did that on purpose. So this project began back in 2015. We looked at a bunch of sediment cores from across the Ross Embayment to try and reconstruct the retreat of the Ross ice shelf from the last glacial maximum. And we didn't really succeed with a lot of those cores. They were very difficult to date. There's a lot of recycled carbon. And so we've got one core that's a really, really good one. There's a poster on that. That's by Louisa Fontenot. She's presenting that. That's probably the only success story from that bunch of cores we looked at. This core here had a magnetic reversal in it. Now, for those that are uninitiated in what a magnetic reversal is, the field flips. And the last time that happened was 780 or so thousand years ago. So that's definitely not a last glacial maximum story as well. So what happened? What does that look like? Well, we have 6 meters worth of mud here. There's some concentration magnetic mineral records here. They wiggle backwards and forwards. This is the magnetic inclination of the field preserved in that sediment. So this is a normal polarity, that's today. And then the field flips, here goes to reverse polarity. So that there is 781,000 years ago. So that puts me at a bit of a problem here. What are these wiggles? I thought, well, I'll do some spectral analysis, which is trying to understand the frequency of the wiggles. And that turned out to be obliquity, which is 41,000 years. And so I knew that if that's a glacial advanced retreat story, which might be an assumption you make, then you'd say, well, that can't be right, because everyone knows that for the last million years or so, ice ages have happened every 100,000 years. 2 problems. The core's not relevant for the study because it's not Holocene, and there's this weird wiggly thing here which I don't understand, so there were too many unknowns. Put the core on hold and forget about it. Well, that was it. Then someone said, oh, why didn't you have a look at that again? So we went back to it again, and that was in about 2019. COVID probably locked us in a little bit, so we looked at that. And then we submitted this paper back in 2020, and then at the start of this year, finally it came out. And that was this story here about how we believe the West Antarctic ice volume changes happened on obliquity timescales until about 400,000 years ago. Now, I really like that figure, thank you, because that 400,000 year marker seems to be something significant for Antarctica. So let's look at the evidence, right? So the last 8 glacial cycles have been paced with eccentricity, fact, and that's from ice cores, isotope, sedimentary records. This is what I was taught. And you look at some of these early publications from the 70s, well before I was born and before, I'm going to say half the room was born here, at a guess. So it's quite a challenge to look at this publication record and say, yeah, I'm probably wrong with this record here. And we look at the ice core, or Epica, 8 glacial cycles, and the base of that core has a date of 800,000 years. So again, I'm thinking, okay, we're probably pushing things uphill here. But then when you look at in detail, someone's probably going to call me out on this, but the early age models were done by comparison to marine records. So how do we reconstruct glacial cycles in Antarctica? We can look at ice cores, we can look at sedimentary records close to the margin. You've got to be close to the action, but not too close. And we can go to the deep sea record here, deep sea oxygen isotopes. Here is a deep sea oxygen isotope stack from Lisicki and Ramo. This is 0, sorry, it's back to front now, from someone else, 0 through to 1.8 million years. If the thing is down here, that means Antarctica, sorry, the world has a lot of ice. If we're over here, the world doesn't have a lot of ice. Low amplitude, high frequency cycles. High amplitude, low frequency cycles. This is the mid-Pleistocene transition here where the world changed apparently. Okay, moving on. Antarctic sedimentary records, so we can go to that here, and sedimentary records, they can tell us about where and when the ice was. We can also look at iceberg raft debris records that tell us when Antarctica's chucking ice into the ocean. And so when you look in detail at the literature, then you can find that there's IODP 1361, that over there. That takes us to 500,000 years, but then the core gets murky after that. And then there's the Andrel record, which has been smudged here, but the top part of that, top 100 years, is not very well resolved. So we actually don't know, when you look in detail, what happened in Antarctica for the last million years, or 1.5 million years. So, to summarise, there's about 10,000 publications on isotope records and Scopus, 5,000 publications on the MPT, and about 565 Epica publications. That's probably out of date. There's probably more now. They're probably right, and this little core here, NBP03, is probably wrong. So what are these quaternary cycles? Let's look in detail. So let's push this core as far as we can. What do we have? What do we need? Is this actually a record of ice advance and retreat? And then are we sure it's quaternary? Always got to keep that in mind. Are we maybe in the Eocene or the Oligocene? So paleomagnetic data look very, very good for, this is data heavy, I'm so sorry, but if it points up, that's norm polarity. If this thing points down, that's reverse polarity because we're at the pole. This reversal is very, very well resolved. The magnetic minerals are very, very good. Now let's look at these little wiggly things here. Are they actually what they are? Are we certain that they're statistically significant? And then are they actually evidence for ice advance and retreat? So we do some really, really good spectral analysis with something known as a Monte Carlo simulation that we run for about 10,000 times, and it tells us that with 99% or greater than 99% certainty, these are obliquity-paced cycles when we use the paleomagnetic age model. And so the beautiful thing about that is that we can actually then filter the data, so we can count the cycles back, and when we look at the phase, which is, okay. When we have high obliquity, we have low magnetic minerals. When we have low magnetic minerals, we have high obliquity. I'll come back to that in a second. But when we do a filter, so this is time down here, 1.2 million years. One of these is obliquity, the other one's the record, and you can see that they're out of phase, so we can even count our way back. So that gives us faith that the age model is actually pretty good. Going on. So we can cycle count our way back. Now this is getting even more awful now. We can do another kind of spectral analysis, which is called an evolutive harmonic analysis. And age is now here, 300,000 years ago to 800,000 years. The top and the bottom bit are missing because of something called an edge effect. You don't have enough data to do an analysis that's statistically significant. And this little thing down here tells us frequency and cycles per thousands of years. Basically, if there's blue and it lines up with the green arrow, that means obliquity is in that part of the record at a particular time. Yeah. So what we have here is an ARM, this is a magnetic mineral concentration record, an XRF titanium, and an iceberg rafter debris record. These two things have been used to generate records of ice sheet advance and retreat. This is pretty rough though, I'll admit. And it was based on counting clasts that are greater than 2 millimeters per section of core, the Talarico method, I'll call it. And so they tell us that, yes, maybe these are all singing the same song, and so we submitted it. We tried. Anyway, let's have a go. 5 rounds of review later, the XRF data were thrown away because some reviewer knew more about that data set than I did, I'll admit, and said it's too noisy. So we chucked that out. Then someone else said, you cannot do clastology, the Talarico method, on such a short core, and I said, okay, fine. So we will do micro iceberg rafter debris. That gives us a much precise, or more precise record. And the paleomag was unchanged, even though someone challenged it at the 11th hour. So what do we have now? Well, so this plot again here, the red band here, and the ARM record, that's unchanged. It's still very, very good. The susceptibility, well, that's another one of these concentration things. The IBRD now is much better, much more well resolved. And this is the Lisicki-Ramos stack, that isotope record, which shows you it's all paced by 100,000 year cycles. And this is a different thing called winter duration. So what we suggested was actually this is the ice shelf front and the West Antarctic ice sheet wiggling backwards and forwards with obliquity. So how does that work? So now this is where we translate that into the ocean. Here's the link. On seasonal timescales, so Stewart et al., they noticed this thing. So this is Ross Island here. And they noticed that the ice shelf melts in the summer and that it's related to how much the ocean warms. So they saw this effect going tens of kilometers underneath the ice shelf, and the carving front actually provides the resistance. So we thought, so this is on seasonal timescales. We've seen now that actually warm water can make it under an ice shelf, and it can be the sun that warms the ocean because it's dark, right? So on these longer time scales, how does insulation, or how do insulation variations translate into the advance and retreat cycles? Well, Huber's, this is someone that I've been following because he keeps bashing on about this, that there should never be eccentricity in a climate record because there's nothing, eccentricity doesn't force anything. So on orbital timescales, Huber's and Denton suggested that Antarctic temperature, so the long summers and short winters, should lead to gradual retreat and vice versa. So if you've got long winters and short summers, the opposite should happen. And so when you do a spectral analysis, again, spectral analysis, but you just look at the insolation variations or insolation at this latitude, where that core is, and at the Ross embayment, that area there, is extremely sensitive to obliquity. there's a lot of power in the obliquity band, and so we suggest that actually the long-term forcing, that long-term control, which is powered by obliquity, is controlling that ice margin and the West Antarctic ice sheet. And so that result also then lines up with the work of Levy and others, where they said that these ice sheets that have got their feet in the water, the marine-based ice sheets, should be sensitive to obliquity forcing. And actually that it probably does work as well, all the way to about 400,000 years ago, if we really look in detail and if we're close enough to the margin, and if we remove ourselves from being influenced. I shouldn't say that, but let's step back a bit, and if you see something you don't understand, don't just say it's probably wrong. It took me about 5 years to get there, but it took us 5 years to get there, that actually this probably isn't wrong. And so that's the ice front there, or the great ice wall that was probably going backwards and forwards for the last, to about 400,000 years ago, paced by obliquity. So summarising all of that, we suggested the West Antarctic ice sheet was driven by obliquity till 400,000 years ago, and that the deep sea isotope stack, I should have said stacked record, is probably overinterpreted at this stage. I think go to a specific record that's close to the action is probably better. And then the last thing is, do we need to keep calling it the Antarctic ice sheet? Why don't we just have the two ice sheets and say different bits of it might be doing different things at different times on different frequencies? Thank you.
We have time for one quick question. Anyone? Yeah, Michael.
Thanks. It's Mike White from Not Nature Geoscience. I'm just kind of wondering, in terms of the sociology of doing this work, did you ever have the feeling that you were putting forth like a heretical idea that post-NPT that things weren't on 100,000-year cycles?
Yeah, I was quite worried actually. That's why I was very happy about the talk when you said there's two different things that are going on here at this ice sheet. But I'm very happy for a whole bunch of other people to publish lots of papers and say we don't find this anywhere else, and then we can think about maybe that forcing mechanism doesn't work in deep time, or maybe it's something else that's doing it, or maybe it's just the ice shelf. Anyway.
Yeah, we'll move on. But intriguing, thank you. Next speaker is Sally Lau.